Today, we are looking at the effects of enzyme concentration on the activity of invertase. So let's just start by looking at enzyme concentration. So first of all, what we have to notice that increase in enzyme concentration will speed up the reaction as long as there is substrate available to bind to. And once all the substrate is bound, the reaction will no longer speed up since there will be nothing for additional enzyme to bind to. And what we also have to note is that we have three main conditions related to enzyme concentration in an enzymatic reaction. The first has to do with low enzyme concentration. The second condition is intermediate enzyme concentration, and the third condition is the high enzyme concentration. So we are going to pick each of these situations or conditions and look at what happens at each stage. So let's look at the first one, which is low enzyme concentration. At low enzyme concentrations, there are few enzyme molecules and excess substrate molecules in solution. So as you can see over here, we have few enzyme molecules with excess substrate molecules in solution. And as there are too few enzyme molecules to allow all substrate molecules to find an active site at one time, the rate of reaction is therefore half the maximum rate of reaction. So what we can see from this graph is that this is the maximum rate of reaction, the point at which the maximum rate of reaction will occur. But from this graph and at low enzyme concentration, we can see that the rate of reaction is half the maximum rate of reaction. So the next condition is intermediate enzyme concentration. So at this condition, we have equal enzyme molecules and substrate molecules. So as you can see from here, the number of enzyme molecules and the substrate molecules are the same. And as this happens, all the active sites of the enzyme will be filled with the substrate molecule at one time to double the rate of reaction as to its maximum. So as you can see over here now, so one thing that we can notice is that all the active sites of the enzyme have been filled with our substrate. So this increases the rate of reaction to its maximum. And this is the nature of graph for intermediate enzyme concentration in enzymatic reaction. And the last is the high enzyme concentration. And what we also have to notice is that the addition of further enzyme molecules results in excess enzyme molecules. So as you can see from here, we have excess enzyme molecules without their active sites filled. So these excess enzyme molecules will have no effect as there are already enough active sites to accommodate all the available substrate molecules. Therefore, there will be no increase in the rate of reaction. So as you can see from this graph, where the maximum rate of reaction occurs after adding more concentrations of the enzyme to our test solution, we can see that the nature of graph still remains the same. That is, the reaction still remains the same. So an increase in an enzyme concentration after the intermediate enzyme concentration will have no effect on the rate of reaction, and this is the nature of graph that it's seen over here. The next is to look at sucrose. So let's talk of sucrose. So first of all, what we have to notice that sucrose, a disaccharide, is a sugar composed of glucose and fructose subunit, and it is produced naturally in plants and is the main constituent of white sugar. It has the molecular formula as the C12H22 and O11, and its molecular structure as this. So this is our glucose unit, and this is our fructose unit, and this is and this is the glycosidic bond between the alpha one of the glucose molecule and beta 2 of the fructose molecule. The next is invertase. So invertase is an enzyme that hydrolyzes or breaks down the sugar sucrose into fructose and glucose. Invertase is also known as sucrose, saccharase, or beta fructofurantosidase. Invertase can be obtained from many organisms, including yeast. Now let's look at the sucrose hydrolysis in an enzymatic substrate reaction. So first of all, what we have to note is that enzyme substrate reaction involves the enzymatic reaction between an enzyme and a substrate. The substrate sucrose has a glucose and a fructose units bonded together, and the enzyme invertase has an active site that allows the substrate sucrose to bind to in this reaction. So what you have to notice that in the enzymatic reaction, the substrate, which is sucrose, binds to the enzyme invertase to form an enzyme substrate complex as seen over here. And the binding of the substrate and enzyme places stress on the glucose fructose bond, and the bond breaks in the presence of water to produce the product glucose and fructose as seen over here. So these are our product glucose and fructose, and this is the enzyme. Also, the enzymatic reaction can also be seen as this. So where invertase in the presence of water is able to hydrolyze or break down the alpha 1 and beta 2 glycosidic bond of the sucrose substrate to produce a molecule of glucose and fructose. Let's now look at the materials and reagents that we need to perform this test protocol. So the first is our invertase obtained from a commercial yeast, and we are to prepare 1% of the invertase in a 0.5 molar acetate buffer of pH 4.5. The second is our substrate, which is the 10% sucrose. The third is our buffer, which is 0.5 molar acetate buffer of pH 4.5. The next is 1% sodium hydroxide. The next is our 10 milligrams per ml glucose standard. That's it. Phospholipid acid, alkaline copper tartrate reagent, water bath set, at 37 degrees Celsius and our UVV spectrophotometer. So let us now take a very good look at the table over here. Now, if we should look at the table over here, we have 5 different test tubes labeled at 0, 1, 2, 3, 4. And over here too, we have our 10% sucrose, which is our substrate, labeled as A, our buffer, our 0.5 molar acetate buffer of pH 4.5, labeled as B, our water labeled as C, and our enzyme, which is the yeast invertase, labeled as D. So what you also have to note from the table is that our substrate is the 10% sucrose, the enzyme is the invertase, the buffer is the 0.5 molar acetate buffer of pH 4.5. And one key thing that we also have to note is that from D over here is that increasing the volume of enzyme in each test tube is the same as increasing the enzyme concentration in the test tube. So as you can see over here, for each of the test tube, we added different volumes of the enzyme. So for the test tube 0, we added 0.0 mils of the enzyme. For test tube 1, 0.5 mils of the enzyme. For test tube 2, 1.0 mils of the enzyme. Test tube 3, 1.5 mils, and test tube 4 to 2.0 mils of the enzyme. So what this means is that an increase in the volume of this enzyme in each of the test tube is the same as increasing the enzyme concentration. Also, A, B, and C forms the substrate buffer. So the 10% sucrose, 0.5 molar acetate buffer, and the water forms our substrate buffer, and D is the enzyme. Test tube 0 is blank since no so test tube 0 will be used as blank since no enzyme is added to it from the table. So as you can see over here, in an enzyme substrate reaction, the reaction will only occur in the presence of a substrate and an enzyme. But from test tube 0, we can see that there is no enzyme added, so there will be no any reaction. Therefore, the first test tube labeled as 0 will obviously be used as our blank in the test protocol. Now, so let's start by looking at each step. The first step is involves the equilibration of our substrate buffer prepared from the table and enzyme at 37 degrees Celsius for 5 minutes. So as you can see, our water bath is set at 37 degrees Celsius for the equilibration, and in the water bath we have our test tube 0, which consists of A, B, C. We didn't add a D over here because D is just 0 mils, and our test tube 1 consists of the materials A, B, C, and D. Test tube 2, A, B, C, and D. Test tube 3, A, B, C, and D. Test tube 4, A, B, and D. And over here too, we didn't add the C to it because C is 0 mils. And this is our enzyme invertase in a different test tube over here. So we equilibrate our substrate buffer and our enzyme in different test tubes at 5 minutes at a temperature of 37 degrees Celsius. So the next is to perform an enzyme substrate reaction, and this is done by adding 0.0 mils of the equilibrated invertase, which is the enzyme, to test tube 0 from from our previous label. To test tube 1, we add 0.5 ml of the equilibrated enzyme. To test tube 2, we add 1 ml of the equilibrated enzyme. To test tube 3, we add 1 ml of the equilibrated enzyme. To test tube 4, we add 2 ml of the equilibrated enzyme. And we have to note, and what we have to note is that the test tubes are still in the water bath at 37 degrees Celsius whilst adding the equilibrated enzyme to it. The next step is the incubation of each reaction mixture at exactly 50 minutes at 37 degrees Celsius. And what you also have to note is that test tube 0 is excluded because there will be no reaction in the absence of the enzyme. So this is our water bath again set at 37 degrees Celsius. And these are the various test tubes that we are going to equilibrate exactly 15 minutes. So we have test tube 1, test tube 2, test tube 3, and test tube 4. So the next step happens to be stopping of the enzyme substrate reaction with 2 ml of 1% sodium hydroxide at 15 minutes incubation. So after the 15 minutes incubation in the water bath, we now stop the enzyme substrate reaction by adding 1%, by adding 2 ml of 1% sodium hydroxide to each of the reaction mixture. So as you can see over here, after 15 minutes of incubation, we pick this test tube from the water bath and add 2 ml of 1% sodium hydroxide to it. After 15 minutes of incubation, we pick this test tube from the water bath and add 2 ml of 1% sodium hydroxide. After 15 minutes of incubation, we pick this test tube from the water bath and add 2 ml of our sodium hydroxide. And after 15 minutes of incubation, we pick 2 ml of our sodium hydroxide and add it to this test tube. So the next step is to dilute the stopped reaction with distilled water in 0.1 in 10 ml dilution. So when we say 0.1 in 10 ml dilution, so what it means is that we will pick 0.1 ml of the stopped reaction and add it to 9.9 ml of distilled water. So for test tube 2, we dilute the stopped reaction by picking 0.1 ml of the stopped reaction and adding it to 9.9 ml of distilled water over here. We do same for test tube 2, test tube 3, and test tube 4. So just try your hand on this question. So how does the 1% sodium hydroxide stops the reaction? Now, so after we are done with the dilution, we subject each test tube to Folin-Wu assay, including tube 0, by picking 1 ml from each tube into a Folin-Wu tube. And I'll also recommend that for a better understanding of the Folin-Wu assay, just watch my video on the Folin-Wu assay. So for the Folin-Wu assay, just pipette 1 ml of the stop reaction, which is the sample, into a Folin-Wu tube. The next is to add 2 ml of our alkaline copper tartrate and place in boiling water bath for 8 minutes. The next step is to cool under running water to room temperature. The next is to add 2 ml of phospholipid acid and gently mix. The next is to make up to the 25 ml mark with distilled water and mix gently. And the last step is to measure and record the absorbance at 580 nanometer. So this is our absorbances after subjecting the stopped reaction to the Folin-Wu assay. So this is our tube 0, tube 1, 2, 3, and 4. And this is the mils of enzyme added to each of the test tube. And these are our absorbances at 580 nanometer after the Folin-Wu assay. So the next thing to do is to determine the concentration of sucrose hydrolyzed by the invertase from the calibration curve plotted earlier. And don't forget that we plotted this calibration curve in the first experiment. So this is the calibration curve for our glucose standard over here, and this is our and this is our line of equation, and this is our R square. So what we are going to do is that we are going to extrapolate our glucose concentration from the calibration curve using the line of equation y equals 1.0331 s. So where y happens to be our absorbances, the 1.0331 happens to be our slope, and s happens to be our concentration. So to extrapolate our glucose concentrations from the hydrolyzed sucrose, we just make s the subject and substitute the absorbance value for each of the test tube as y and find s. So this is the table for the extrapolated glucose concentration from the calibration curve. So as you can see over here, this is the volume of enzyme, the absorbance at 580 nanometer, and these are the extrapolated concentrations from the calibration curve. So we can see that at 0.0 mils enzyme, we have 0.0 mils of milligrams per mil of the extrapolated glucose concentration. At 0.5 mils of the enzyme, we had 0.361 milligrams per mil of the extrapolated glucose concentration. At 1 mil, we have 0.375 milligrams per mil. At 1.5 mils, we have 0.377 milligrams per mil. And at 2 mils enzyme, we have 0.379 milligrams per mil. So let's try to solve these questions. Okay, so the first question says that we are to calculate in milligrams the reducing sugar produced per hour per 10 mils of the reaction mixture, assuming fructose reduces the same amount of reagent as glucose. So that is the first question. And the second question says we are to plot a graph of rate of enzyme activity against volumes of enzymes in 10 mils reaction mixture. So let's see the solution for the first question that says we are to calculate the rate of enzyme activity. Now, so the equation that we are going to use to calculate the rate of enzyme activity is giving us the glucose concentration over the time in hours times volume of reaction mixture. Now, so what you also have to note is that our time is constant throughout, and that is the time of incubation, so which is 15 minutes. So we convert this 15 minutes to hours because it says times in hours. So 15 minutes in hours is the same as 0.25 hours, and the volume of our reaction mixture is also constant throughout, which is 10 mils from the table. Now, so at 0.0 milligrams per mil concentration, so we have our rate of enzyme activity in milligrams per mil as 0.00 milligrams per hour. So at 0.365 glucose concentration, so we have our rate of reaction, our rate of enzyme activity at 0.361 all divided by 0.25 times 10. So we have our rate of enzyme activity at 0.144 milligrams per hour at 0.375 milligrams per mil concentration, we have our rate of enzyme activity to be 0.150 milligrams per hour. At 0.377 milligrams per mil concentration, we have our rate of enzyme activity to be 0.151 milligrams per hour. And at 0.379 milligrams per mil concentration, we have our rate of enzyme activity to be 0.152 milligrams per hour. Now, so this is our table showing the results for the calculated rate of enzyme activity. So as you can see, we have the volumes of enzyme and we also have the measured absorbances and the extrapolated concentrations and the calculated rates over here. So at 0.0, so the rate is also 0.0. At 0.5 mils volume of enzyme, the rate is 0.144. At 1 mils, the rate is 0.150. At 1.5 mils, the rate is 0.151. And at 2 mils, the rate is 0.152. Now, so the next question says we are to plot a graph of rate of enzyme activity against volume of enzyme in the 10 mil reaction mixture. So we are to plot a graph of enzyme activity. So this is the enzyme activity against the volumes of enzymes in mil. And as said earlier, the volumes of enzymes in mil is the same as the enzyme concentration. So if we are to plot our rate of enzyme activity against our enzyme concentration or the varied volumes of enzyme, this is the nature of graph that we are going to get seen over here. Thank you.